샛별.
So what is Faraday's law of induction? It is simply known as Faraday's law, which is a basic law of electromagnetism, which helps us to predict how magnetic field will interact with an electric circuit to produce electromotive force, also known as EMF. So this phenomenon is called electromagnetic induction. To put in simpler words, it is when a changing magnetic field induces an electromotive force in a conductor, and this is based off Ampere's second law. So Ampere's second law is also another fundamental law of electromagnetism. It relates the magnetic field circulating around a closed loop to the electric current passing through that loop. So what is Ampere's second law? Ampere's second law is a line integral of the magnetic field around a closed loop, and it is equal to the free space variability multiplied by the total current enclosed by the loop. So for our experiment, our objectives are to study and also verify Faraday's law of induction by observing the voltage induced in the second coil due to the changing magnetic flux generated by an AC current in the primary coil itself. So the apparatus used during the experiment were two coils of copper wire representing primary coil and also the secondary coil, a lighter, a sandpaper, function generator, oscilloscope, digital multimeter, and crocodile clips.
In this section, I will be explaining the theory behind our experiment, which focused on Faraday's law of electromagnetic induction and its relationship with Maxwell equations. I will also walk through the mathematical derivation that connects these concepts directly to the experimental result we obtained. Faraday's law, a fundamental principle in electromagnetism. Faraday's law states that when there is a change in magnetic flux through a coil, an electromotive force or EMF is induced across it. E equals minus d phi b over dt. Here, E is the induced voltage or EMF, and phi is the magnetic flux. Negative sign indicates the direction of the induced EMF as described by Lenz's law, which the induced EMF opposes the change in magnetic flux that caused it. Magnetic flux of phi b is defined as the total magnetic field passing through an area. In its general form, magnetic flux is defined by the equation. Phi b equals the integral of b dot dA, while b is the magnetic field and dA is a small element of the surface area. The magnetic field is uniform. The equation simplifies to phi b equals b times A times cosine theta. B is the magnetic field strength, A is the area of the coil, and theta is the angle between field and the normal to the surface. In our experiment, the time varying current in the primary coil produces a changing magnetic field, which creates a changing flux in the nearby secondary coil, and that's what caused the induced voltage. Maxwell's third equation. Equation is del cross E equals minus partial B over partial T. This equation explains the same idea but in terms of electric and magnetic fields. A changing magnetic field creates a circulating electric field even without any wire. This is the fundamental reason we see voltage induced in our experiment. Let's now apply this theory to our actual experimental circuit setup. We start by converting the input voltage from peak to peak value to peak value. Hence, the input voltage supplied by the function generator is input voltage equals peak voltage sine omega t. By using Ohm's law, we calculate the current through the primary coil, where Z is the impedance of the coil, I0 is the peak current. We move forward by applying Ampere's circuit law to determine the magnetic field created by the current in the primary coil. We assume the coil is long and cylindrical, with no fringing effect at the ends. This gives us a symmetrical magnetic field surrounding the coil. According to Ampere's law, the line integral of the magnetic field strength around a closed loop is equal to the enclosed current. This can express as the integral of H dot dl equals the enclosed current. Because of the cylindrical symmetry, we simplify this to H phi multiplied by 2 pi r equals input current. Solving for the magnetic field strength H, we get H phi equals input current divided by 2 pi r. This is the magnetic field intensity around the coil. Next, we convert the magnetic field intensity to the magnetic field density B. This final expression gives us a magnetic field generated by the current in the primary coil, and it clearly varies with time. The time-varying magnetic field is what produces a changing magnetic flux in the secondary coil, which leads directly to the induced voltage we measure in our experiment. Let's bring together everything we have discussed into the final form of Faraday's law and show how it connects directly to our experiment. We start with the general form of Faraday's law. Next, we substitute in our expression for the magnetic field just now. Taking the time derivative gives us a cosine term. Then, we integrate over the area of the secondary coil, which is dimension L by D. We also know that omega, the angular frequency, also equals to 2 pi f, where f is the frequency of the input signal. This final equation shows that the induced voltage is directly proportional to the frequency. This is essentially what we observe in our experiment. We apply an alternating current to the primary coil. As the frequency of the AC increased, the magnetic field changed more rapidly. That faster change caused a faster rate of change of magnetic flux, which led to a higher induced voltage in the secondary coil.
I am Law Pei-Chin. Now I will talk about the procedure part of the experiment. So first, we made two coils, which is a 300 turns primary coil and a 150 turns secondary coil using the copper wire. The tips of the wires were cleaned using a lighter and the sandpaper to remove the insulation off and ensure a good electrical contact. The primary coils were connected to a function generator and channel 1 of the oscilloscope to monitor the input signal. The secondary coils were connected to a digital multimeter to measure the induced voltage and to channel 2 of the oscilloscope to observe the waveform. So we placed both coils close together without touching to maximize the magnetic flux linkage. A 3.5 volt peak-to-peak sinusoidal AC signal was set on the function generator, and we verified the frequency from 100 Hz to 5,000 Hz. And so for each frequency, we recorded the induced voltage shown on the multimeter.
I'd like to present about the findings of the experiment. This part shows the data and the results of the experiment to prove Faraday's law, and the table are the readings of induced voltage at increasing frequency. We can notice that there is an increase in VEMF when the frequency of the input voltage F has increased. There are total 16 data recorded in this table to make the experiment to be more accurate. Next is the waveform observed on the oscilloscope. The yellow graph shows the input voltage signal at voltage peak to peak 3.5 volt, while the green line shows the induced voltage VEMF in the secondary coil. Notice that there is a lagging in the sine wave of VEMF graph, whereby VEMF is a cosine wave. This is identical to the formula that we have derived at the theory part. And we can notice that when the input voltage Vin crosses 0 from negative to positive, there's a slope which contributes to the changing drastically of the magnetic flux. Thus, VMF, the green graph, hits its maximum amplitude at this point, while the input voltage Vin reaches its peak. The slope is equal to 0. Thus, there is a minimum change of magnetic flux, causing VMF to be 0 at this point, and when the voltage input crosses 0 downwards, the magnetic flux changes the fastest. Thus, VMF, the green graph, is at maximum value here too. This has proved the Faraday's law, whereby the induced voltage VMF is proportional to the rate of change of magnetic flux. However, there's an issue to prove the Lenz's law. According to the Lenz's law, VMF should be negative peak value when Vin crosses 0 upward, and it should be positive value when Vin crosses 0 downwards. However, this phenomenon does not show in our oscilloscope. This issue might be caused by the probe of VMF being reversed here, leading to the reverse of the observed polarity in the induced voltage waveform, making the VMF appear to be in phase with the Vin instead of opposing the Vin direction, which has a field to show the theory predicted by the Lenz's law. And we have used the 16 data in the table to plot this graph, which is the graph induced voltage VMF versus the frequency of the voltage input. Firstly is the linearity. The R-square value is equal to 0.9439. It is approximately to 1, indicate a strong linear relationship between the induced voltage VMF and the input frequency F. Next is the formula. The formula has the M value, which is a slope equal to 0.0313. It has proved that the induced voltage VEMF is directly proportional to the input frequency F, as stated by the Faraday's law. As the input frequency increases, it also increases the induced voltage VEMF. However, there is an issue to prove the Lenz's law. The proportionality can be proved via the theoretical formula, whereby the proportionality should be negative. However, in this data, according to the data, the slope is a positive value. This positive value is due to the reading of voltage values on the digital multimeter, as it provides the root mean square voltage value in AC mode, leading to the ignorance of the polarity in the induced voltage. This has caused the digital multimeter to always show the positive values, even though the value should be negative.
Conclusion of Faraday's law of induction. So from the experiment, we successfully verified the Faraday's law of induction. The induced voltage increased as the frequency increased. This shows the faster the magnetic field change, the greater the induced EMF in the secondary coil. So the oscilloscope showed that the induced voltage lagged by 90 degree consistent with the theory. However, due to the reservoir probe or multimeter limitation, the expected negative side of Lenz's law was not clearly observed. So for the error improvement, the error include the reversal probe polarity and slight coil misalignment. And to improve, we can check probe dynamic carefully using the calibrated equipment and also keep the coil aligned consistently. That's all from me. Thank you.